Okay, and then we need to make this big.
So you can
Okay,
see the slides, right?
yeah.
Okay, awesome. All right, so I guess we can start. Let me, okay. So the goal of this presentation is to give a broad overview of my modeling work that I'm guessing most of you are a bit less familiar with. So that being said, this is quite a lengthy presentation, like perhaps like 45 minutes, but that's totally fine if we don't get to the end of it. So feel free like to interrupt me or ask any questions. All right, so I'm going to give a brief overview of what we will cover in today's talk. So I will start with a brief introduction, laying out the research questions I've explored in the past. Then I will present my work on spoken language modeling from Clean Speech. So for context, spoken language models are like ChatGPT-like algorithms that are trained on speech instead of text. So following that, we'll go a bit further and train our spoken language models on the speech children receive using child-centered audio. And as we will see, our observations will raise an important question. What do children have that our models don't? So I've started exploring three different directions. I've been working on integrating early speech processing capabilities into our models, evolutionary inductive biases, and equipping our models with the vocal tract. And finally, I will conclude with future directions. All
Sorry,
right.
Marvin.
Yeah.
What about eyes?
Eyes.
Yeah, what do babies have that these models don't?
Yeah, eyes it would be a good answer. Some models have eyes, but I mean we can discuss that at the end of the presentation. For this presentation, my models will be blind, so no
Okay.
eyes. All right. So for the most part, I've been looking at the question of language. So how can we humans master this complex hierarchical structure where sounds combine into words, which themselves combine into sentences? So how can we master this structure that is quite unique to humans and that connects to nearly all aspects of human cognition? So from a broad perspective, the central question I started exploring is like, what are the necessary ingredients required to learn language? So in particular, I looked at the learning mechanisms, the quantity of exposure, and the type of input required to learn language. And I addressed these questions using an interdisciplinary approach, combining artificial intelligence with language development in intents. So more specifically, part of my research was dedicated to building automatic speech processing models using supervised learning methods. So as you know, with this model, we can analyze massive quantities of data to study language acquisition. So for that, to develop these models, I used big databases of child-centered recordings. So the idea is to equip the child with a microphone that collects the audio as people engage in their everyday activities. So in particular, I built a speaker diarization model, the VTC, that identifies who speaks when, a model that estimates the number of words produced by adult speakers, and a model that estimates the quantity of background noise and reverb in the recordings. But I'm not going to
And
talk
Marvin,
about,
sorry, are
yeah,
those the senses in which it's supervised, the first two, or are
the
there
all of
senses in
them,
which?
all of them.
Wait,
So basically, yeah,
what do you mean
these
all of them? So we've got the who's talking when, and how do the sounds group into words?
So basically, like the idea is like to train these models on human annotated data. So like human experts that have tagged the audio for like the task we want to solve. So speaker diarization, who speaks when, and those kind of things. And so basically, by feeding the model with large databases that have been annotated for this specific task, we can train them. And at the end, like we have like automatic annotation tools that we can deploy to large scale databases.
Mhm.
But yeah, all of them are supervised. in slightly different ways. But I mean, yeah, I don't want to focus on that for this talk. But I mean, if you have any questions, of course, like feel free to ask. So yeah, what I'm gonna focus on is my work on infant-inspired self-supervised language modeling. So basically, the idea consists of simulating language acquisition, so building models, computational models of language acquisition using language models, so ChatGPT-like algorithms. So in this talk, in particular, I will explore three questions. So first, what do spoken language models learn when trained on a quantity of data that is equivalent to that of children? Then we'll go a bit further and ask the same question, matching both the quantity and quality of data. And we will do that by training LMs directly on the speech children receive. And finally, I will ask, what do children have that our models don't? So before we begin, it's important to have a rough idea about the quantity of speech children receive. So here you have the distribution of estimates of the yearly quantity of infant-directed speech, and these varies quite a lot, with infants receiving up to 1,000 hours of infant-directed speech per year, and others receiving only up to 70 hours per year. So we'll keep that in mind, as this will help us fix the quantity of data in our simulations. So we also need to look at what infants learn. So here I'm presenting some of the developmental milestones during the acquisition of sounds and words in infants, so during the first year. So regarding the acquisition of sounds, we know that 6-month-olds discriminate native sounds as well as non-native sounds. And it is only at the age of 12 months that we observe an increase in infants' capacity to discriminate native sounds, and a decrease in their capacity to discriminate non-native sounds. So basically, in this short time span, 6 months only, they become language-specific listeners. So this is like Cool's experiments and so on. So regarding word learning, on average, we know that infants start to recognize their own name at 4 months. At 6, they recognize the auditory form of frequent words. And for their third birthday, they typically comprehend around 80 words. So what this timeline shows is that infants learn about the sounds and the words of their native language in a gradual and parallel fashion. They don't learn the sounds first and then the words, or vice versa. They learn at both levels at the same time. And this is what I'm gonna try to simulate using spoken language models. All right, so I'm going to present a first study on spoken language modeling from clean speech. So the idea is to build a learning algorithm that reproduces early sound and word learning in infants. So here's the approach. We have a model of the environment, so the information the child receives, a model of the learner, so the learning mechanisms, the mechanisms responsible for learning, and a model of the learning outcome, so how we measure the language capabilities of the model. So this is akin like to how we measure language capabilities of infants in the lab. So for this first study, we used large quantities of English or French audiobooks, and the idea is to simulate the development of an English learning or French learning infant. Regarding the learner, so this is like full of technical details that I don't think are super interesting, but briefly, we used a self-supervised learning algorithm that works from raw speech, so not text. And it is made of an acoustic model, contrastive predictive coding plus k-means, trained to predict the near future of the near future and to discretize the audio. So basically, the acoustic model takes the raw audio as input and outputs discrete representation of the audio. So a series of discrete numbers. And then we have the language model that receives the discrete representation of the audio as input, and that is trained to predict the next unit. So I guess like the important idea behind this model is that it learns by predicting the near future of the audio up to 120 milliseconds, being given the past context. And it is like fully unsupervised and it works from the speech stream. So basically that's a model of kind of like from the sensory stream, which is the speech stream, to behaviors that take place in the learning outcomes. So at test time, like when we want to test the learning outcomes of the model, we used two tasks that are directly inspired by how we evaluate human language capabilities in the lab. So in the first task, the phonetic evaluation, we evaluate the model's sound discrimination capabilities. And in the second task, the lexical evaluation, we evaluate the model's capability to recognize the auditory form of words. And I will give more details about the evaluation now. So,
Sorry, Mark.
yeah.
Sorry, this is the lexical. This is the
Yeah,
phonetic. Okay, fine, sorry, I wanted to ask about the
we have
phonetic.
like
Yeah,
one phonetic evaluation, one lexical evaluation.
sure.
Yeah.
Marvin, can I
Yeah.
ask you a really basic question about the previous slides? Would it be okay if you went back one? Thank you. So you're trying to build an agent which learns language similar to a human infant, right?
Yeah.
Mm.
So basically, maybe like another way to explain like what I'm trying to do is like I'm trying to see which mechanisms can explain the developmental pattern we observe in infants, which is like this parallel learning across the sounds and the words.
That makes sense. I'm just wondering, like, so in the next slide,
Yeah.
there's this stuff where, oh, sorry. There's this stuff about predicting the next unit.
Yeah.
I guess I wonder a little bit what the role of that in a infant's language learning is. Like, why?
Yeah, that's an excellent question. So I guess like, I mean, this is one model among like thousand other possible models, but I guess like this is an implementation of the idea that like the brain is trying to infer what's gonna happen in the really near future. And actually it's like super easy to do, you know, like if I stop like at the middle of the sentence, you're gonna be able to predict like the next sound maybe, and maybe the next word as well. So yeah, this is an implementation of this idea, which I think is compatible with what we know of infants, but I'm happy to debate.
That makes sense. Oh, sorry.
Sorry, Marvin, just out of interest, because this is something I often do when I'm talking to early years teachers. I always make this point from the point of view of prior language knowledge, helping to pay attention to speech in noisy settings. But what I always worry that I don't really know what the evidence for that is. Sorry, not to get too off topic, but what is the evidence that, you know, so there's lexical violations, yeah? So you get the brain has a bigger response to something that's semantically incongruous. What other evidence is there that this represents some fundamental aspect of how our brains process language?
So about infants, I'm not actually sure because I think this paradigm, I think we can call that a paradigm, is quite hard to study in infants. But basically, this is a theory that has received the attention of the neuroscience community. This is like it's called like a the predictive processing hypothesis, like something like this. And people have attempted like to find like neural correlates of that theory, like to find like neural traces of like the human brain trying to predict like speech stimuli, for instance. But so yeah, I guess like this is like the most compelling evidence we have for that. But I mean, as with like any other mechanism, it's like super hard to prove that it is real, you know, that I mean that's just a theory. And we could argue that it's not because like we show that this is true like in the lab with like cherry-picked stimuli that it is necessarily how the brain works in more naturalistic settings.
Lexical violations are proof of that theory, though. if I have a bigger brain response to a word when it's embedded in a sentence where it's incongruous compared
It
to.
is, but I think the theory is more general than just the lexical level.
Oh, I see. Yeah, you could do phonemic. I can see why that's.
Or vision as well. Actually, it's like a learning mechanism you could implement on the visual stream as well, like trying to predict like what's the next frame is going to be or those kind of things. But you're right that lexical violation is like, I mean, we could consider it as like a trace of like, yeah, of that theory.
Marvin,
Can I keep going?
I was hoping I could ask, this is much more basic, but is the reason that, so I noticed there's like this emphasis in the test, in the outcomes about like predicting, I guess is the idea that infants understand language when they can pass a speech stream and successfully predict what the next token is. Is that like the idea behind, or the model of success that these sorts of models have?
I'm not sure I would use words like understanding. Yeah, I'm not sure I would put it like that. I guess like the idea is like if you have like a learning mechanism that consists in predicting the near future, it can lead to knowledge or like to behaviors that resemble those of humans.
Oh, okay. So it's not necessarily this is how the baby is doing it, but it's this will produce a
Well, we don't
successful.
know how the baby is doing. You have like, but again, like I have like a slide about that at the end of the presentation. So
I'm sorry.
maybe we can discuss that at the end of the presentation. But yeah, for now, I would say that like in reality, like we don't know how children are doing, and like this is, I guess, like one way to explore one hypothesis among like 1,000 other possible hypotheses. Does that make sense to you?
That makes sense. Thank you.
Awesome. All right, so the phonetic evaluation, so we use an ABX paradigm that is used actually like to evaluate sound discrimination capabilities, not in infants, but in adults. So in this task, the machine is being given three spoken triphones, so for instance, lip, lop, and lip. So we compute their representation via the acoustic model. So basically, we give lip and like in an audio recording that contains lip to the model, and the model returns a bunch of numbers, which are called representations. So basically, in this task, the machine succeeds if the distance between the two occurrences of the same triphones is smaller than the distance between the two occurrences of the different triphones. So lip and lip, which are two different occurrences of the same triphone, must be closer to one another than lip and lop. And finally, like one thing we cannot do with children is that like with machines, we run that on millions of triphones over all possible contrast in English or French.
Question.
Yeah.
Sorry, what's the unit of that?
What are you referring to when you're talking about units?
What's the unit of distance?
All right. So actually yeah, that's a really precise technical question, but I think it's like a super important question. So you can choose the distance, and it depends on the kind of representation you're working with. But basically, like for instance, we could say we could use like a Euclidean distance, but we know that this distance doesn't behave in a really good way with high dimensional representations. So we use the cosine distance, which is another kind of distance.
Thank you.
Yeah. So now the lexical evaluation. So for the lexical evaluation, we use the spot the word task, in which the machine is being given a word and a pseudo word that sounds like a real word. So a pseudo word that whose phonotactic probability is matched to the real word. So for instance, The model receives cookie, which is a real English word, and kuni, which isn't an English word, but it sounds like an English word. We compute the probability of each stimuli via the language model, and the machine succeeds if the probability associated to the real word is higher than the probability associated to the pseudo word. And again, like we run this procedure on thousands of pairs in English or French. Do you have any question on the spot the word task?
Is it going to succeed at that just because it's heard more instances of the real word?
Okay, can you say that again?
So it will have just heard more instances of cookie, and that's how it's going to know that that's a real word.
Yeah, but that's the idea. I mean, the model wouldn't have received any utterances of kuni because it doesn't exist in English. Yeah, but yeah, that's the idea. Like you're gonna receive a bunch of words during like the developmental phase, and then at the end of the at the end, like we evaluating whether you can recognize a real word from a fake word, basically.
Okay.
But basically, this requires to learn like long-term dependencies or like medium-term dependencies. It's like longer-term dependencies than in the phonetic evaluation. It's not. I don't think it's like a task that is too easy. I mean, that is easy actually. Yeah. I don't want to give too many details, but so especially like so we built the pseudo words so that they are matched with the words in unigram and bigram probabilities of phones. So basically you cannot solve this task if your model is a unigram or bigram model over the sequence of phones. But in any case, we don't have access to the sequence of phones because we work with the speech stream. I'm not sure I was super clear, but anyway. So we follow the methodology that is used in psycholinguistics. So basically, we use a cross-linguistic design in which we train a model on English, a model on French, and we evaluate them on their native language. So this is on native condition, but we also evaluate them across languages. So this is on non-native condition. And so basically, the idea is that comparing performance across the native and the non-native conditions allows us to measure what the model has learned due to exposure to its native language as compared to exposure to another language. So in other words, the non-native model it acts as a baseline, or like it's like the control condition. All right, so about the results. So here you have the phonetic score computed on the ABX non-discrimination tasks for models trained on varying quantities of speech. So here we limit ourselves to 3,000 hours of speech, which is equivalent to the quantity of data children receive during the first 3 years. Remember the graph I presented earlier. So what we observe is that with more exposure, models become better at discriminating sounds, and this is true in both the native and the non-native conditions, which makes sense. So basically, being exposed to English also helps you discriminating French sounds. Yeah, that makes sense because like you have many common sounds across these two languages. And interestingly, what we observe is that the gap between the native and the non-native model increases with the quantity of speech. So the gap between the two curves, which means that the English model becomes progressively better at discriminating English sounds compared to the French model and vice versa. So regarding the lexical accuracy computed on the spot word task, we observe a performance improvement only in the native condition. So the native model learns to recognize the auditory form of words. However, the non-native model does not learn to solve this spot word task as shown by the relatively flat dashed line. And again, this
Marvin,
makes
So the sound discrimination, did you look at, are there particular phonemes that is it because you'd expect obviously that the phonemes that are
Yeah.
common between English and French,
Yeah.
it doesn't make much difference in the phonemes that
Yeah.
aren't. It does, but that would be quite an easy thing to test, right? I just wondering if you
Yeah,
test-
yeah, definitely. You can study like the sound the percentage discrimination contrast by contrast. So we looked at it, but I have a few results about that in the second study, not in this study, and on English and Japanese, for which we have more results in infants. So I think it's going to be more interesting to talk about that. Yeah, on English models and Japanese models.
And presumably also the variance at a low quantity of speech, the variance is very high, and
Yeah, quite
presumably it
high.
would be quite easy to look at what drives that variance. There's some when you just have a small amount of speech, some of the speech must be much more useful than other bits of the speech for
Yeah,
learning.
yeah, that's an interesting question. So basically, like the variance I'm showing is computed from models trained on different training sets, so different environments in a way. And so it seems that there are some environments that yields to better speech sound discrimination capabilities than others. But this can be due to other factors as well, like because I mean in machine learning, like when we train a model, it's if we train a model twice, like yeah, we won't have the same model at the end. It's not deterministic. Yeah, so I think that's it. So yeah, so in a nutshell, with these two graphs, we show that our model reproduces the gradual and parallel learning across the phonetic and lexical levels that I was talking about at the beginning of the presentation. So similarly to infants, our model learns at the sound and the words level and the word levels in a gradual and parallel fashion. All right, so next we look at what kind of information is present in the learned representation. So what does the model learn? So we consider the acoustic model and we examine whether phonetic categories structure the learned representations. And basically this is linked like to the whole debate in language acquisition on whether infants like have like phonetic categories or not. So we observe that representations are separated according to sonority, which is a measure of loudness. Regarding consonants, they are separated according to the place of articulation. We observe that consonants are also separated according to voicing. So this is TS-INI plots. So in a nutshell, it seems that the learned representations at the phonetic level are relatively abstract and they share some common properties with phonetic categories, although our model has never received any phonetic categories. The goal is like to learn these categories. Yeah. So we run a similar analysis on the language model for lexical categories. So this time TS-INI analysis do not reveal a clear separation between function and content words, nor do they for part of speech categories. However, we use like a different technique to evaluate our model, which are linear probes. So basically you trained a linear classifier on top of the learned representations and you evaluate whether this linear classifier can discriminate between different classes. So we do that for function versus content words and for part of speech categories. And so interestingly,
Marvin, sorry to interrupt, Marvin. Can you just explain just for everybody? So TSME, it's flicking through lots of different ways of dimensionalizing the data, right? And then it's not finding any ways of dimensionalizing it that differentiates. Would you just want to explain how
yeah, definitely.
What the axes are when those plots on the left?
So I mean, the axes are quite hard to interpret. But so basically, the representations learned by the model are like 256 dimensional vectors. So you have like 256 numbers, which are like super hard to analyze. This is way too complicated to analyze. So what we do like to visualize like the information contained in the representation is that we use what we call dimensionality reduction techniques. So basically, you transform your 256 dimensional vector into a 2D vector that shows some kind of clusters if you're lucky. I mean, if your representation contains some kind of information, yeah. Okay, what's important to know is that like this is unsupervised. So because an easy way to, an easy way to do it would be to like transform your representations into a 2D vector using like a supervised technique. Like so you actually force the model to separate across part of six categories, let's say. But this is not the case of TSNE. So yeah, it's just a way of visualizing what type of information is contained in the representations. So about the
fine.
linear probes, so we see that so although like TSNE do not reveal any separation, it seems that the learned representations contain information about function versus content words and part of switch categories, although the accuracy of the linear probe is not really high. And so one important information is that in both cases, we observe a positive effect of data quantity. So the more data the model receives, the more information about lexical categories it contains. So the model builds up lexical knowledge, let's say, yeah. All right, so to wrap up on this first study, so our question was like, what do language models learn when trained on the quantity of data equivalent to that of infants? Or children would be more appropriate because like it's from 0 to 3 years old. So we showed that they learn about the sounds and words of their native language. They learn representations with some degrees of abstraction that are structured along linguistic categories. And they reproduce some developmental patterns observed in infants. So in particular, we showed that that they learn about the sounds and words of their native language in a gradual and parallel fashion, and they become language specific. I mean, they develop like this language specific perceptual space with the English model becoming progressively better than the French model at discriminating English sounds. And they do all of that with no supervision. So yeah, basically, yeah. To conclude, like, so I guess like the first conclusion is like, so first, spoken language model might be good models of early language acquisition since they can reproduce these developmental patterns. And the second conclusion is basically like statistical learning like from extracting statistics from the speech stream is sufficient to explain this gradual and parallel learning trajectory we observe in infants. It's sufficient to explain early sounds and word learning. I mean, if we assume that early sounds and word learning consist of discriminating sounds and recognizing the auditory form of words. I guess you have many questions, right?
Yeah, Marvin, can I ask quickly? I know you have another study to present, but do you think there's like a
I have
limited
3 other studies to present.
Sorry, I'll be very, very quick then. Do you think there's like a limited capacity to those models? As in, do you think if you're switching halfway between the English and the French model, you could like mimic bilingual development of language when like initially it's a bit slower, maybe, but then it catches up? Or do you think the models are not like big enough to just learn all of those patterns?
Yeah, that's a really cool question. I think it's like a super interesting topic, like but bilingual acquisition. So I haven't studied that, but when I was doing my PhD, another co-PhD was like focusing on this question, like what happens when we train models on multiple languages, on two languages, which were English and French. And she showed that, so yeah, there's some kind of like capacity limits and basically performance of the bilingual model in terms of sound discrimination was lower than monolingual models. I don't know if that reflect anything about infants. Yeah, I'm not an expert like in this literature, but it might be possible that like if you have to learn two languages at the same time, then it takes a bit more time to discriminate the two sets of sounds belonging to these two languages. Yeah,
I
and
just
maybe
got
like yeah.
No, what were you going to say, Marvin? Were you going to
No,
more on
go
that?
ahead.
Just quick, is there anything you say in terms of what this learns about the passive perception of sounds? Is there anything it doesn't explain?
I
Because
mean,
obviously there's so much that you're not including in this. I'm just
yeah,
curious.
definitely. I
Yeah.
mean, well, basically, I would say that it doesn't explain anything that I haven't presented today. We don't have evidence. So, for instance, like something that I was a bit disappointed about. So, we evaluated the model at the syntax level, which is even harder because you have to model like long-term dependencies, like at the scale of the utterance of the sentence. And what we showed is that these models perform at chance level for syntax. Whereas like 3-year-olds, you know, like they have a quite good understanding of the syntax of their native language. So yeah, for now it seems that this type of models struggle with syntax when trained on speech. So that's one example, but you have like a thousand other phenomenon that I guess would not be reproduced by these models. I wouldn't expect them to develop any semantic, for instance. Like I don't think, but this is personal belief. I don't think it's possible to learn the meaning of words being only given the speech stream. I mean, yeah, only 3,000 hours of speech. Yeah.
It's just got
Yeah. Okay.
I have a
Okay.
question.
Yeah, go ahead.
Oh, sorry, if you're in the middle of something, I can wait. It's a
No,
beginner
no.
question. This is a really beginner question. But I'm just wondering, once you've created a model, once you've finished working on a theoretical model like this, where do you deploy it so that it could be tested or used more broadly? Like, let's say that if someone else had a data set and they wanted to see if your model could predict the findings that they had or could capture
Yeah.
or explain something about them, where would
Yeah.
be a place that could happen?
Yeah. Well, that's not a beginner question. I think this is probably something we need to work on a lot more. So basically those are like quite theoretical models that are shared like via GitHub repositories, but the code base is quite complicated. And basically like I wouldn't expect, for instance, like psychologists to be able to use these models and to test hypotheses, for instance, with this model. And I think they could do it, but it requires strong programming skills. And that's a shame because I think like it limits the impact of these models. Yeah,
Okay, thank you. That was my question.
that was a good question.
Marvin,
All
just
right.
so we've got 15 minutes left, yeah, and there's a few of us who've got to leave exactly at 4, I'm afraid. So do you just want to pick what else you want to do? It's lovely to have lots of questions as ever, but just pick what you want to do, then we'll have another session to do the other half, okay?
I mean, I don't mind if we don't do the other half, but I'd like to present the next study and like I will jump to the conclusion, if that's okay for you. All right. So one big limitation of this first study is that we used audiobooks, and this is an unrealistic assumption. Like children don't learn language from audiobooks, and this is obvious to anyone. So yeah, the next question is like, what happens when we place this kind of model in an environment that is similar to that of infants? Poof, poof, poof. And so one way to do so, like to place these models in a child environment, is to use long form, so recordings collected using child one microphones that I was talking about at the beginning of the presentation. So here yeah, there's like some audio, but we won't have time. It's just like we use Lina like long forms that collect the child's language environment. And as you can imagine, it's like super noisy. They contain close field as well as far field speech. They contain a wide array of environmental noises, and people like may sing, like mumble or shout. Like this is naturalistic speech. So really different from audiobooks. So another difference between long forms and audiobooks so at least in our data sets we found very different language uses. So for instance, we found a lower proportion of speech in our long forms, and we found a higher proportion of female speakers in long forms than in audiobooks. So in child data, you are like female speech is more present than male speech. Because like we use like an English and French data set. And we also found like a much shorter turn duration. In long form, speakers alternate much more frequently than in audiobooks. You have differences in terms of recording conditions as well. So we used a Brouhaha that I mentioned earlier, the model to predict the speech-to-noise ratio and the C50. So comparing long forms with audiobooks, we observed that long forms have a much lower speech-to-noise ratio, indicating a higher level of background noise. And same for the C50, long forms have a much wider variety of reverberant conditions, whereas audiobooks contain clean speech. So yeah, the question I'm asking is like, what happens when we train our models on the audio children receive? So for this study, we used the exact same model as before, and we trained it on either audiobooks or long forms. So here you have the phonetic score using the same ABX on discrimination task, and the native advantage, which measures the extent to which the native model is better than the non-native model. And so what we found on audiobooks is that the model progressively learns to discriminate sounds, and the model develops a language-specific perceptual space with the native model better at discriminating sounds than the non-native model. So basically, those are the same results as before. What's interesting is like to look at what happens when we train our model on child-centered long-form recordings on the speech children actually receive. So on the left graph, we observe that the native phonetic score plateaus after 64 hours of audio. And on the right graph, we observe that the model fails to develop a language-specific perceptual space. So in this case, the English model discriminates English sounds as well as the French model. So really, like we're looking for this basic property of like, if you're exposed to English, you should process English sounds better than someone exposed to French. And when we train our models on long forms, this is not what we observe. Yeah. And so conclusion of this second study, and then I would jump to the conclusion of the presentation. So training on long forms, we showed that models, spoken language models develop very shallow speech sound discrimination capabilities, with the native discrimination plateauing after 64 hours of audio. And they fail to develop a language-specific speech sound discrimination capability. Yep. And we showed, although like it hasn't been shown in the presentation, we showed that they fail to learn at the lexical level. These models trained on naturalistic data, they cannot solve the spot the word task. So basically, like the hard lesson, which is disappointing but quite expected, is that this fancy model that seems to reproduce developmental patterns observed in infants when trained on audiobooks, they don't reproduce these patterns anymore when we train them on naturalistic audio. And so basically this raises the question, what do children have that our models don't? A very interesting question that I won't have time to address today. So yeah, basically I've started exploring 3 different directions. A direction Sam mentioned is like maybe these models lack visual capabilities. So yeah, but what I want us to spend at least 5 minutes is bluff. Okay, so basically the long-term perspective of like my work, and I'd love to have your feedback on that. But so yeah, basically like the goal is like trying to find like what is the good recipe, and maybe there are many different recipes for learning a language, for language acquisition. So basically, some researchers think that perhaps infants rely mostly on statistical learning, so tracking event frequencies from the speech stream. This is best exemplified by the work of Safran. Perhaps they rely on cross-situational learning, so tracking well-referent co-occurrences. So this is, for instance, the work of Linda Smith. Or perhaps they rely more on social learning, so learning through social interactions, joint attention, and so on. So for instance, like this is Tomasello. Or perhaps another hypothesis is maybe learning altogether is not so important, and what drives language development is innate factors. And this is represented by Chomsky and his language acquisition device. So of course, like these different theories of language acquisition are not mutually exclusive. Like, and actually, I think everyone agrees that infants and children use all of these different mechanisms. What people disagree on is like the respective contribution of these different mechanisms. And so basically, all the theories that put forward the role of learning emphasize the contribution of the environment, while nativist theories emphasize the role of the genes. And I think one way to study the contribution of the environment on language acquisition is to run input-output analysis of child-centered recordings using automatic tools, so the VTC and other tools. So basically, if we do that on large-scale databases, we can run models like so y as a function of x, with y the language skills of the child, and x different variables of the environment, such as like the speech quantity, the number of word reference, or the number of joint attention interactions, for instance. So basically, this is how we can use AI as a tool to study language acquisition. All right, and ideally, we would go even further and implement each of these theories into computational models. And this way, we could evaluate which learning mechanisms lead to which language skills, which would basically help us better understand what's going on with infants and young children. And yeah, so this is basically the conclusion of this really long presentation.
Yeah.
Right, round of applause to Marvin. Right, we've got, well done for doing that. So Marvin, I'd love to hear the second half of that, the bit you skipped over. So do you mind just putting Marvin down for another slot at some point? Yeah. Okay, we've got a few minutes of questions.
Very quick question. So your model relies only on statistical learning, right?
Yeah, for the models I presented, statistical learning only. But I've worked actually quite a lot on nativism, which I think is like quite interesting because this is not often mentioned by people who are doing computational models. But I think there are ways to explore the importance of innate factors in computational models. But basically, this was in the part of the presentation that I haven't presented. But what I haven't worked on is like, yeah, cross-situational learning. So basically equipping models with eyes, or social learning. And cross-situational learning, I think we can run like many super interesting experiments. Social learning, I think it's much harder to simulate in a convincing way. Yeah.
Yeah, there are quite a few aspects that you could do for social learning.
Mhm.
Many of them done by people in the room.
My question would be, what is the relation between learning languages and reading from birth on? Because the statistics shows that if the children have specific number of their own picture books, they are reliable for the age, that the acquisition of the language goes much different way, faster than the kids have books only from the library, starting when they go to nursery, meaning 2, 3 years old. And how and what is then the influence of eye contact, reading to the lab, confronting, having the picture, and the recognizing languages with the images on the book? Because audio learning is only listening. So
Yeah.
it is only one channel of sensation coming to the body.
Yeah. But I think like this is exactly the type of questions that can be addressed by computational model. So I don't have an answer to your specific question because I haven't studied that. But basically what we could do is like we control the proportion of like storytelling interactions between the child and the caregiver, and we see how this impacts the learning outcomes of the computational model. We see if like storytelling sessions help the model learn faster, for instance, or learn specific aspects of language that couldn't be learned otherwise. Yeah, this is typically the kind of like what we could call like ablation experiments that computational models can address.
Thank you.
Yeah.
And any more? I've got one more for no one else. Just
I was just wondering if, like, do you have ideas for how to simulate, say, where you're providing that naturalistic audio as input? I'm guessing for the actual infantness that was exposed to that, there's going to be parts of that they're not necessarily learning from, but then the parts that they really may be really learning from are the bits that are addressed to them in response to something that they've produced, or vocalizations that they're making. And is there ways to simulate that? I can't really think of them, but so if you so the model is kind of producing something, making some prediction, and then it's hearing response that would be more related to that prediction.
Yeah. So I guess like this boils down to like how can we simulate embodiment?
I mean, not just
it could be, but but it could just be just speaking, and then
so
like you could do the same thing from just hearing a child. Like I don't know if it was to be embodied and actually socially interact.
Or like tamarins do, they also have contingent vocalizations. So when babies make an adult-like utterance, the adult contingently repeats the utterance in a mature way.
Yeah.
That reinforces it. Is that the kind of thing? Because I can see, I guess, pretty easily how you might combine that with some model like this. Like, so when the model predicts something adult-like, it's reinforced, and when it's not reinforced.
Yeah. But do you agree that this requires embodiment? So basically the model is producing an output, like a speech-like or a non-speech-like vocalization, and then the caregiver reacts appropriately to this stimuli.
Yeah. Good. Well, that was really great, Marvin. Yeah, we'll get you back. Sorry, Pierre's just put something which I thought was an answer to Gio's comment, but I think it's a yeah, that's a question which you can talk about later. So Marvin, have a look at that and email Pierre. But another round of applause for Marvin. Really lovely work.
Thank you for the questions.
And then to be continued. Thanks,
Yeah.
Marvin.
Thank you.
And then, yeah, and we'll look forward to, yeah, we'll look forward to doing that.